Today we're going to finish up Chapter 5 by looking at our linear models. So we're going to focus on in this section and look at our linear models. Right? So when real-world relationships are described using a function, we call the function a mathematical model. In this section, we are going to focus on linear models. In this section, kind of the ideas that we're using here, it comes up in a few problems that you may have encountered in Chapter 3 if you took Math 95. And then what we're going to talk about in this kind of next problem that we're going to look at also shows up in statistics. We actually, in Math 126, spent an entire chapter talking about these types of problems. And then if you take 115 and you study the statistics chapter in 115, the idea of linear modeling also comes up in one of the sections that you would see in that class as well. So linear models and finding these linear models are very important in statistics, which again, if you take 126 and possibly 115 next semester, you may run into these again. Right, where we're going to start, we are going to start by thinking about something called a scatter plot. Right. A scatter plot is created by plotting all ordered pairs associated with a set of data. The scatter plots that we're going to look at in this section are going to be created using technology. In this particular example that I have in our notes, I actually used Excel to create the scatter plot. But there are different ways of going through and doing these, different programs you can use, different functions that you can use. Scatter plots are not limited to straight lines. We could have scatter plots that turn into something that looks like a quadratic shape or an exponential shape or some sort of non-linear shape as well. We're just choosing to focus on our linear models. All right, so underneath here, remember that our linear equation of a line in function form is f of x equals mx plus b. Right, m is our slope, b is our y-intercept. We saw a reminder of this in the previous section at the end of section 5.2, and that we also calculate our slope of our line m equals y2 minus y1 over x2 minus x1. All right, so what we see down at the bottom, right, is a set of ordered pairs and a corresponding graph or image that goes along with this. Right, so we see a relationship between our time studied in minutes and the test grade, which is given as a percent. Right, the way this is set up, looking at both our graph and our set of ordered pairs, our first column is representing our x values along our horizontal axis, and our second column is representing our y values, which we're going up the vertical axis. A lot of times in statistical scatter plots, unless negative numbers are of some sort of value, we just kind of focus on our first quadrant and we look at all positive numbers most of the time. In most real-world applications, that is going to be the case. Not necessarily all, but oftentimes. All right, so we're going to use these images and this idea and these ordered pairs to answer the next few questions. Right, so on the top of the next page, our first question says, discuss the relationship shown in the scatter plot. Right, so what type of relationship is shown? Right, so looking at this picture, again, it's not perfect, and we actually see this line presented in here. Right, what we have, our data appears to fall in a pretty nice straight line here. So that means that this would be an example of a linear model or a linear relationship. Again, if it was something that was curved or something that was nonlinear, right, we could have other shapes. In this case, this is a linear relationship. Is it increasing or decreasing? Well, looking at this, as we go to the right, we are going up. Right? So this is an increasing linear model. Right? Increasing and decreasing are also going to go along with our slope in our particular question. Right? So since this is increasing, we should expect to have a positive slope. Right? The next example, what is the linear function that represents this data? Right? So here's where creating our equations of lines that we revisited in the last section is going to come into play. Right? So in order to come up with an equation of a line, we need to have two different values. We need to have two different ordered pairs that we're going to use. So looking at this, I'm going to pick 2 points that look like they are very close to being on this line. Right? So I'm going to highlight and use this point here, right, and this point here. They look very, very close to being actually on our dotted line, right, that was given to us in this graph. Right, now using our x and y axis, right, we are very close to 60 here, and we are close to or at 60 up here. So looking in our table, that means that this first point is going to come from this ordered pair. It's going to come from the ordered pair 57, 60. Right. Now if we look at this last ordered pair, well, we're close to 140 and 100. Mm-hmm. So that means that this is going to be our other set of coordinates for our ordered pair, 140 and 98. So we start by picking out a couple of points in our data set that are going to look like they're close to being on our line. Right? So then we're going to use these values to generate our linear equation. Right? So we're going to start by finding our slope. So m equals y2 minus y1 over x2 minus x1. Right? And we're going to use, right, that set of ordered pairs that we have up there. Right? So I'm going to call this x1 y1 and this one x2 y2. Right? So y2 minus y1 is going to be 98 minus 60 over x2 minus x1, 140 minus 57. That's going to give us 38 out of 83. That's a fraction that can't be reduced here, so we're going to switch it to a decimal, and I'm going to round that decimal to 3 place values, so 0.457. Right, now that we have our slope, we're going to find our equation of our line. Right, so we're going to use y minus y1 equals m times x minus x1. Right, so y minus 60, right, that was our y1, is going to be equal to 0.457 times x minus 57. Right, so again, we're using that same first ordered pair there. Okay, so now we're going to go through and work out the arithmetic. Y minus 60 equals 0.457 times x. So we'll drop to parentheses. We're going to distribute that decimal. Times x minus 0.457 times 57 is going to give us 26.049. Right, now we want to get y all by itself, so we're going to add 60 to both sides. Y equals 0.457x. Right, if we take negative 26.049 plus 60, we get plus 33.951. So our linear function is going to be represented by f of x equals 0.457x plus 33.951. Notice that our slope is positive, right? So our line was increasing, so this positive slope does match with that. Right, now the last thing that we're going to do is we're going to use our equation that we just found to make some predictions. So we are going to predict the test grade if we study for 1 hour, and then if we study for 2 hours. Right, so using 1 hour. 1 hour is 60 minutes. So we are going to plug 60 minutes into our function. Right? F of 60 is going to be equal to 0.457 times 60 plus 33.951. Do your multiplication and then add. We get 61.371. Right, so our predicted test grade, if we study for an hour, right, our predicted test grade would be about a 61. Predict the test grade if we study for 2 hours. 2 hours is 120 minutes. So f of 120, 0.457 times 120 plus 33.951. F of 120 turns out to be 88.791. So if we study for 2 hours, we have a predicted test grade of about, or approximately, if we round it off, an 89%. So the idea is, depending on the type of data set that we have, if we have a data set that is linear in shape, right? So looking back to our data values, they seem like they created a straight line. We can use those values to come up with an equation. Again, if you take a statistics course or study the idea of a linear model in the future, there are actually more sophisticated ways of finding the exact equation. This is an approximation, right? Models are approximations, so there's not 100% accurate, right? Which is one reason that we kind of round, and so we say the predicted test grade would be, right, about 61% or about 89%. We don't have exact values. We cannot say anything for certain, but based on this linear model, we can at least generate something that's close, an equation that's going to be close, that fits our data set, and then make predictions based on that equation as well.